Welcome to the fascinating world of probability. Today, we are diving deep into one of the most fundamental yet misunderstood concepts in statistics: independent events. In simple terms, two events are independent if the occurrence of one does not change the probability of the other occurring. Imagine the universe as a series of gears. For independent events, these gears are not connected. Let's start with the most iconic example: flipping a fair coin. If you flip a coin and get heads, what is the probability that the next flip will also be heads? It remains exactly 50%. The coin has no memory. It doesn't know it just landed on heads. Statistically, we say that event A, the first flip, and event B, the second flip, are independent. According to the law of large numbers, while we expect a 50-50 split over thousands of flips, each individual flip is a fresh start. Mathematically, the definition of independence is elegant. Two events A and B are independent if and only if the probability of both occurring, the intersection, is equal to the product of their individual probabilities. This is written as P of A intersection B equals P of A times P of B. If this equation holds true, the events are independent. If P of A intersection B is anything else, some form of dependency or correlation is at play, often requiring conditional probability calculations. A classic way to visualize this is through replacement. Imagine a jar with 3 red marbles and 2 blue marbles. If you pick a marble, look at it, and put it back, replacement, the probability of picking a red marble on the second draw remains 3 out of 5. However, if you keep the marble without replacement, the total number of marbles changes to 4 and the ratio changes. This simple act of putting it back is what maintains independence between trials. Let's apply this to the real world. Quality control in high-tech manufacturing, like at an Intel or Apple facility. Suppose a machine has a 1% chance of producing a defective chip. If the production of each chip is an independent event, the probability of 2 chips in a row being defective is 0.01 times 0.01, which is 0.0001 or 0.01%. This helps engineers set safety thresholds and predict failure rates in massive data centers. In genetics, independence is seen in Mendelian inheritance. If 2 parents are carriers for a recessive trait, the chance of their first child inheriting it is 25%. If they have a second child, the chance is still 25%. The genetic coin toss for the first child does not influence the second. This is why some families might have 3 children with the same rare trait, while others have none. Each birth is an independent event in the eyes of probability. Beware of the gambler's fallacy. This is the mistaken belief that if something happens more frequently than normal during a given period, it will happen less frequently in the future, or vice versa. In a game of roulette, if the ball lands on black 5 times in a row, many people bet heavily on red thinking it is due, but the wheel doesn't remember. Each spin is perfectly independent. Ignoring this leads to millions of losses in casinos every year. To conclude, understanding independent events allows us to see through the illusions of patterns where they don't exist. Whether in finance, science, or daily life, distinguishing between what is connected and what is independent is key to rational decision-making. References: 1. John E. Freud, Mathematical Statistics with Applications. 2. Sheldon Ross, A First Course in Probability. 3. Damodar Gujarati, Basic Econometrics.